Euler's method or Euler's method, the basic idea behind direction fields can be used to find numerical approximations to solutions of different equations. We illustrate the method on the initial value problem that we use to introduce direction fields. Y prime equals x plus y, and y of 0 equals 1. The differential equation tells us that y prime of 0 equals 0 plus 1 equals 1. So the solution curve has slope 1 at the point 0 and 1. As a first approximation to the solution, we could use the linear approximation big L of x equals x plus 1. In other words, we could use the tangent line at 0 and 1 as a rough approximation to the solution curve. See figure 11. See figure 11. First, Euler approximation, solution curve, and y equals big L of x. Back to the text. Euler's idea was to improve on this approximation by proceeding only a short distance along this tangent line and then making a mid-course correction by changing direction as indicated by the direction field. Figure 12 shows what happens if we start out along the tangent line but stop at x equals 0.5. This horizontal distance traveled is called the step size. Since big L of 0.5 equals 1.5, we have y of 0.5 approximately equals 1.5. And we take open 0.5 and 1.5 close as the starting point for the new line segment. See figure 12. Euler's approximation with step size 0.5. Back to the text. The differential equation tells us that y prime of 0.5 equals 0.5 plus 1.5 equals 2, so we use the linear function. Y equals 1.5 plus 2, open x minus 0.5, close equals 2x plus 0.5 as an approximation to the solution for x is greater than 0.5. The green segment in figure 12, if we decrease the step size from 0.5 to 0.25, we get the better Euler approximation shown in figure 12. Shown in figure 13. See figure 13, Euler's approximation with step size 0.25. Back to the text. In general, Euler's method says to start at the point given by the initial value and proceed in the direction indicated by the direction field. Stop after a short time, look at the slope at the new location, and proceed in that direction. Keep stopping and changing direction according to the direction field. Euler's method does not produce the exact solution to an initial value problem. It gives approximations, but by decreasing the step size and therefore increasing the number of mid-course corrections, we obtain successively better approximations to the exact solution. Compare figures 11, 12, and 13. For the general first order initial value problem, y prime equals big F of x and y, and y of x sub naught equals y sub naught. Our aim is to find approximate values for the solution at equally spaced numbers at equally spaced numbers x sub naught plus x and x sub 1 equals x sub naught plus h. X sub 2 equals x sub 1 plus h, where h is the step size. The differential equation tells us that the slope at open x sub naught and y sub naught close is y prime equals big F open x sub naught and y sub naught closed. So figure 14 shows that the approximate value of the solution when x equals x sub 1 is y sub 1 equals y sub naught plus f, restarting that line, y sub 1 equals y sub naught plus h big F open x sub naught and y sub naught close. Similarly, y sub 2 equals y sub 1 plus h big F open x sub 1 and y sub 1 close. In general, y sub n equals y sub n minus 1 plus h big F open x sub n minus 1 and y sub n minus 1. See figure 14. You have the slope f of x sub naught and y sub naught, and you have the point x1 and y1, and you have h, and f of x sub naught and y sub naught. Back to the text. Euler's method or Euler's method approximate values for the solution of the initial value problem. Y prime equals big F open x and y closed. Y of x sub naught equals y sub naught with step size h at x sub n equals x sub n minus 1 plus h, or y sub n equals y sub n minus 1 plus h big F open x sub n minus 1 and y sub n minus 1 close. N equals 1, 2, 3 ellipses.